present our CVPR project titled Bridging Low Supervision Challenges and Open Set Domain Generalization in the. So in this particular paper, we basically try to tackle three major challenges. One is the low shot learning, where there is typically very less number of examples or samples for each of the closed set classes. And then also the open set recognition, where the model encounters new classes that it has not seen during the training period. And lastly, we also have a domain shift in which the training distribution as well as the testing distribution differ drastically. So even though there are existing methods which basically tackle this problem in isolation, in realistic scenarios, all of these challenges can fulfill. So our major goal is basically to develop a unified prompts learning technique which can tackle all of these three challenges simultaneously. And this is basically done through an attribute learning setup plus targeted open sample synthesis. So what I meant by pseudo open sample synthesis is that our closest competitor, which is ODG Clip, generates pseudo open samples for the particular dataset by using a prompt called a photo of an unknown class. And we can see that the pseudo open sample synthesis through that particular prompt is quite unrelated to the task that we are trying to solve. And this is particularly important in the tasks such as low shot setting, where there's typically very less number of closed set samples. So we basically try to do a targeted pseudo open sample synthesis in a way like we prompt the GPT-4o to generate all the class names that are very close to the specified closed set of classes in the dataset. And in this way, we get a list of all the classes, and then we pass that to the stable diffusion. We can see that the generated images are much more related to the task that we are trying to solve when compared to the previous methods. And this will help the model to make a more informed decision boundary. Now, we also do an attribute generation, and the reason why we do this is because this will help the model to do a better understanding of the image, especially in the case where there are very few images for each of the classes. And how we get to do this is again we prompt the GPT-4o model to generate all like k number of distinguishable attributes for that particular category. So this are a few of the sample attributes that we kind of sort out for each of the classes. It is for dog, it is for snout, tail, and paw pads. And this is done for all the classes that is present in a particular dataset. So now this is our proposed method. So now we make use of all the pseudo open samples that we have synthesized previously, as well as the attributes for each of the classes. Now, there we use kind of a multi-model prompting technique. And the reason why we do this is because this helps to bridge the gap between the textual learning and the visual learning, visual prompt learning. And there are kind of three losses that we kind of use, which is the domain generic prompt and the alignment loss and the domain specific loss, cross entropy loss. And the domain generic cross entropy loss is basically made to tune the domain agnostic prompt, which also involves all the closed set of classes and the unknown category. While in the domain specific cross entropy loss is basically used to tune the cross attention layer, which is used to enhance the domain specific prompt, which is for each of the domain categories that is present in the dataset. And this is kind of trained with this domain specific cross entropy loss is used to train this cross attention layer. And then we have the alignment loss, and the alignment loss is used to make sure that the domain agnostic prompt embedding is equidistant from the embedding that is generated for each of the domains in the source domains. And this is our entire proposed setup, and we basically report our results on five major domain generalization datasets. And the metric that we use to report the results is basically the closed set accuracy and the harmonic score. And the harmonic score is basically the harmonic mean of the closed set accuracy and the open set accuracy. This us to ensure that the model does good in both the closed set as well as the open set method. We have seen that our model does well when compared to previous methods in both one shot as well as a five shot setting. We also do an extensive ablation study whereby we try to do the different possible variations in the domain-specific prompting as well as the domain-agnostic prompting. And we also try to vary the number of attributes that is present per process. So before we pass it through the cross-attention layer. And we also do an ablation study on the variation of the each of the three loss terms. And then we see how effective is our targeted open sample synthesis. We also do an ablation study on what happens if we increase the number of shots or a number of closed set and open set classes. And most importantly, we can also see that our model is quite efficient with respect to the number of parameters when compared to previous efforts. And so, in conclusion, our method is one of the first to jointly tackle low shot learning, open set recognition, and domain generalization through a unified prompt framework. So, we believe that this will open new directions in data vision and robust vision language learning. Thank you.